Assalamu alaikum, dear students. I'm very happy to be back with you with another video lesson. In the previous video lessons, we covered Unit 6, and of course it was one of the longest unit you can say. But I really hope it was worth it, and I really hope that you practiced very well, and I hope you mastered all the concepts. Today we'll start with something very different from Chapter 6 or Unit 6, and today we'll talk about interference. So we will be going through what is interference, and after that, basically that is, we can say, Chapter 7. Or before we begin with that, let me just tell you what are the contents of this chapter here, or the chapter previews to be more specific. We'll talk about, okay, that is clearly Chapter 7, you can say interference and diffraction. So we will begin with interference, that is the first part that, or first section that we will be going through. And then after that, we'll talk about diffraction. And of course, hopefully you can see, at least you have an information about what we have here. That is beside each, you can say, content or chapter preview. And then the end of this chapter will be about lasers. So we'll talk about lasers and, of course, those colorful, you can say, unified or directed light beam that are called lasers here. Okay, so the first thing to begin with, we will talk about interference. So what is interference? Have you ever seen, for example, the colors on a, let's say, bubble soap? Right, what is the difference between this and, of course, those colors that you have seen, let's say, or those colors that come out from a prism, let's say? Of course, there is a huge difference between the two, you can say, yeah? And of course, we can say, or if I go through this one, you've probably noticed the bands of, the bands of colors that form, let's say, on the surface of a soap bubble, you can say. And of course, this is very different from those colors that we said, those colors that we get, let's say, or we see that that are emerging from a prism, because that'll be, or those colors will be due to, you can say, refraction or bending of light. But those colors, of course, we get them as a resultant of wave interference, or more to be more specific, you can say the waves of light after they interfere. And of course, these are the colors that we get. So this is what is called interference. And as you can tell from the word interference, when we have, or it happens when waves interfere with one another. Okay, so of course, we've studied wave interference in chapter, or you can say sort of this, or at least a part of this in Unit 3 as well. We said waves, of course, let's say, can interfere constructively or destructively, or of course could be weakening as well, which is part of the destructive interference. So that is basically what we have. Combining light waves, that is what we get as a result. Okay, now interference takes place between waves with the same wavelength. What do I mean by this? Let's say if you have two waves, of course, let's say one of them is red, the other one is green, or let's say it could be any other colors, yeah? These, or you can say interference, let me make it short. Interference will not take place between two different frequencies. So if you want interference to take place, you must have waves that have the same frequency. And of those waves, when we say the same frequency, if we, of course, regarding the speed of light, let's say, then those two waves must have the same wavelength as well. So when two waves have the same wavelength and frequency, then of course these two waves will interfere with one another. But of course, sometimes could be constructively, some other times could be destructively. So let's go through what happens exactly when two waves interfere with one another. So if two waves with identical wavelengths interact, they combine to form a resultant wave. And that is what we have said, or we've learned before. The resultant wave has the same wavelength, and this is something very important. Okay, so one thing to note is this one here. What happens, or what it changed here, I'm going to write this one perhaps, or give it a bit of extra explanation on the whiteboard here, but let me just tell you this first of all. When two waves interfere, the only thing that changed here is basically their amplitude. So their frequency, or you can say the wavelength, will always remain the same as long as, let's say you have two waves interfering that have the same frequency, let's say. And remember, if they don't have the same frequency, then there will be no interference. Okay, so according to the superposition principle, the wave's displacement at any instant equals to the sum of the displacement of the component waves. In a different way, we can say the resultant displacement, or you can say the resultant amplitude, will be the sum of all vectors. So if we have, let's say, peak and peak, or let's say bottom and bottom, if these two coincide together, let's say, then of course we'll add them, but if they are in opposite direction, we normally subtract them. Okay, so the resultant wave is the consequence of the interference between two waves In interference, energy is not lost, you can say, but it is, or instead it is redistributed here. Okay. So now we have something, a term before we proceed. It is called monochromatic or single color. What is monochromatic? We normally use this term for those colors or those waves, let's say, that has a single frequency and wavelength, let's say, or just simply for those, we call it monochromatic. Chromatic would be for the color, mono, that would be one or single. So of course, when we have a single color here, of course, let's say the single color might be just because or due to one single frequency. That is why we call it monochromatic here. Okay, so a single color, it is a light source that has a single wavelength, like what? Like a laser light here. So we're not talking about a combination of two colors, and of course, you get a third color. That is not what we want, yeah? Or that's not what we're talking about. We're talking about a light color that has only a single wavelength, you can say a single frequency, and of course a wavelength too. So now we can talk about the types of the interference. The first one that we have, it is called constructive interference. What is constructive interference? Let's demonstrate these, okay? Giving you some information about each one of these here. So let's say we have, or let's say the first one here. So we have, remember, in order for constructive interference to happen, you have to have, let's say, two wavelengths, and then let's say two waves, and these two waves, let's say they must have the same frequency. So let's say this is one of the waves that I have. Okay, that's too much, but still, okay, maybe these drawings are not very precise, but as long as, for the sake of the explanation, of course, you will have an idea. Let's say I have another wave here. Okay, that is too much. Let's make it a bit smaller so that we can make the resultant a bit bigger. So let's just make this one this much here. So you can see that these two waves, of course, you can say these are in phase here. Okay, these are not perfect drawing, but of course, I think it is good enough to see the results. So we have two waves here. You can call them wave 1 and wave 2, yeah? So let's call this one wave 1, okay? And of course, let's call this red one wave 2 here. So what would be the case here now? So let's say this is number 2 here. So now you can see here, these two waves, of course, you can see here, these are the peak, you can say. Okay, so we have crest and trough, yeah? So the crest of this one kind of like coincide, overlaps the crest of the other one here, the trough and trough, crest and trough. Or you can say top and top, bottom, bottom, peak and peak, let's say bottom and bottom. So once we have this, the first thing we know that, of course, these two waves have the same frequency, because you can see, okay, they cover the same, you can say, or they have the same frequency. So having the same frequency, that means these are in phase. That is one of the things, yeah? And of course, one more thing here, how do we know whether these two waves interfere constructively or destructively? You can see these are both at this side. If we take this half only, you can see that these are above the equilibrium. So we're just going to add them here. So we will get a resultant wave, and let's draw the resultant wave in black, and of course make this one a bit, let's say, thicker so that you know what it is. So let's say this is the resultant wave that we get. Now this, let's just make it a bit more precise here. Of course, now the resultant wave will have, okay, need to make it a bit better here. Okay. Maybe these are not very precise, but okay, so this black, of course, now let's fix this part a little bit so it makes or looks more convenient. Okay, now you can see these are basically, we have two waves, and the third wave is basically the resultant of these two. So if I have, we'll say the amplitude of the total is going to be, of course, amplitude of wave 1 plus amplitude of wave number 2. If we have more than two waves, of course, if we add, let's say, amplitude of the third wave, and of course, and so on. So this is basically what happens. So we can say, oh, what are the properties of this wave? It is very important to know that, or the resultant here, that the wavelength and frequency of the resultant wavelength, that is exactly the same as the individual waves. That is the key point here. You might just say, because these two, or you can say their amplitudes would add up, you might also say their wavelength would be doubled as well, but that is not the case. It will be incorrect if you say the wavelength will change whatsoever. So what happens here is their amplitude will add up or increase. You can say it becomes this. You can see that this amplitude, of course, it is the sum of these two, or you can say that it is bigger than both of, or you can say each one of these individual amplitudes here. In terms of the frequency and wavelength, of course, it doesn't change. You do know that the wavelength, you can say from the peak to the, from the crest to the crest, peak to peak, bottom to bottom, that is trough to trough. And of course, you can start at any point on a wave to the same exact point on the next wave, that is one wavelength here. And of course, regarding the energy, you can see that the energy of the resultant wave, of course, it is bigger than, or it is the sum of the energy of the individual, you can say, wavelength here. Okay, so that is normally for what? That is normally for constructive interference here. So the waves must be in phase. That is the key, you can say, the condition for the constructive interference. The component of the wave combine to form a resultant wave, which is basically has the same wavelength, but with an amplitude that is greater than the amplitude of either waves, you can say, or the individuals. Okay, for light, we have the resultant, or if you can say the result of a constructive interference is light that is brighter than, let's say, the light from the contributing waves here. Now we have destructive interference, but in terms of destructive interference, we have two types of destructive interference. The first one, it is called weakening interference, you can say. Okay, so if it is weakening, it's going to be something like this. Let's say this is one of the waves that I have. Okay, that is, let's say, one, and then the other one here, let's say I have another wave. This other wave could be, let's say, this much. Okay. The last part, I need to fix this one here. Let's say this is basically, this is what I have. If I put numbers here, I'll say, let's say for the red one here, possibly, let's say this is 1 unit and this is 2 units. Let's just say 2, okay? And for this one, let's say it is just 1 unit. So what will be the resultant of this wave? We can say, for the amplitude, by the way, you can see that these two are, of course, you can see that the phase difference of these two, of course, you can see that it is 180. But why don't they cancel each other out completely? Because you can see there is a difference in their amplitude here. So they don't completely cancel one another out. So we can say the resultant amplitude is going to be the amplitude of the bigger wave. Let's call it number 1 here. And of course, 1 is the amplitude of the second wave here, because this is bigger. So as a result, we will get this amplitude here. Let's use green this time. So we will get something like this here. So this is what we get as a result. So this green one, of course, it is representing the resultant amplitude. And of course, you can see this green, it is, you can say, or the amplitude of the resultant wave, it is smaller than the amplitude of the bigger wave. We cannot say it is smaller than both of the, or the amplitude of both of the waves. Why? Because you can see that these two are not, or you can say that this is not smaller than this one. So it would be best if you just say the resultant amplitude is smaller than the amplitude of the larger wave, you can say, or the wave that has a larger amplitude. That'll be better to say. So what happens to the energy of the, let's say, resultant wave? Of course, it is going to reduce, because in these two, of course, they partially canceled one another out here. So that'll be this. And of course, you can see that it has the same wavelength and same frequency. That is basically what is called weakening interference. What about total destructive interference, let's say? If it is total destructive interference, that'll be a different story. So what will be that in this case? So once again, let's say we have two waves here. One of them, let's use this. So let's say one of them, it is basically, we can say 2 units upward, and then the other one is 2 units downward, you can say. The phase difference, or the condition for total destructive interference, must be this. The waves must be out of phase by 180 degrees. Okay, that is this. And of course, their amplitude also must be the same, or there has to be they have to be the same in amplitude as well. So you can see if this is 2 units, let's say 1 and 2 unit upward, this is also 2 unit downward. Yeah? So you can see that this amplitude is the same as this. So what happens as a result? These two waves will completely destroy one another. And of course, we get this one as a result here. So let's say this is now the resultant wave here. So you can see that these two waves completely cancel one another out. And that is, we call this one destructive interference. So what happens to the resultant amplitude? We'll say amplitude 1, 1 is amplitude 2, and of course this is equal to 0 because they have the same amplitude, but one of them you can see it is, you can see that the crest of this one kind of like it is exactly or overlaps with the trough of the other one. So these two, of course, completely cancel one another out, and as a result we get this one here. So you can see here, there is no wave left, you can say here, yeah? That is called destructive interference here. So if it is, by the way, when we have destructive interference, if it is, for example, that happens for the light, of course, especially if it is on a screen that later on we are going to study, then of course you will see a dark spot on the screen. That means there is destructive interference. If it is constructive, that is going to be a brighter spot. If it is partial, of course, you get a light that is neither, let's say, too bright or not dark, something in between, which is going to be a dim light. So what are the properties of each one of these here? We went through this one. What about this one? Completely or destructive interference. The interference takes place between only between waves with the same wavelength. So we set that one condition before, so it is the same for all the types of waves here. Whether if it is total constructive, let's say, or constructive, partial destructive, or complete destructive interference, the waves must have the same wavelength, otherwise it doesn't take place. Okay, so but for this one here, if you do remember, for constructive, we said the phase difference must be 0, or it could be, let's say, could be 2 pi or 4 pi or whatever, yeah? As long as we have, let's say, one whole number of a wavelength, or it could be 0. And then, of course, we get a constructive interference there. And then, but for destructive, the phase difference between the two must be 180 degrees, okay? So we'll say the waves must be out of phase with a phase difference of 180 degrees. And then the waves must have the same amplitude. What happens if they don't have the same amplitude? Let's say one of them is 4 up, the other one is 2 down. Of course, they get partially destructive, or will be partially canceling one another out. We get a partial destructive interference. Okay, but if they have the same amplitude, one is up, the other one is down, of course, then we will get a total destructive interference. And of course, we'll demonstrate or we'll explain on this one as well. And then the amplitude of the resultant wave is 0. Why? Because they both cancel one another out. For light, the result of a destructive interference, of course, that is a dark spot if it is on a screen here. So take a look at this too. We have constructive and destructive. Okay, there's no partial destructive interference. I just want to focus here. For these two waves, of course, we have the same frequency as you can see here, the same wavelength. So the peak, and of course, we have the peak, or you can say the trough against the trough of these waves. So what happens as a result of this? So these two, of course, will be added together. So we get this one here. And of course, for these two, there are, like, for example, their trough, of course, will be added, but you can see below the equilibrium point. So this is basically what happens. We can say this green is a resultant of this right here. What about for figure B here? You can see that these two waves, of course, they're out of phase. This is, you can see, in phase. Huh? You can see that these are in phase, as of course you can see here up and down. You can see these are in phase. But for this one here, this basically, you can say the crest, while the trough right on, you can see that overlapping one another. Okay, so, or you can say, let's say coincide or whatever you call it. So for this one as well, we have a trough, we have a peak. So what happens as you add these two together, this is the resultant that you get. You can see the amplitude is 0 here, and that is why we call it a destructive interference, because they completely destroy one another. Okay, that is for constructive and destructive interference, which is nothing new to you because you've covered this in chapter 3. Now, we have this question here. It says, what happens if two lights with the same amplitude interfere constructively, and what happens if they interfere destructively? We said if they interfere constructively, that means their amplitudes will add up. Okay, so as a result, of course, this is what we get. So this amplitude here, you can see that it is bigger than the individual amplitudes of these two waves here. And of course, the same thing for the trough. Okay, so it doesn't matter if it is up or down you take, that is the same. What if they interfere destructively? And of course, these two, they'll have to be out of phase, so they totally cancel one another out. And of course, then the resulting amplitude is 0. If it is for light, for constructive, we get a bright spot. If it is for light and we have destructive interference, we get a dark fringe or fringe here, you can say. So the resultant amplitude will be twice the amplitude of the individual light waves, if they have the same amplitude, of course, producing a bright fringe. Yeah? But for the destructive, of course, is going to be 0 amplitude and dark spot on the screen. Okay, or you can call it dark fringe. Now we have few terms. It says waves must have a constant phase difference for the interference to be observed. Now that is something very important here. Okay, so in order to see the interference, or to observe a continuous interference, the wave, or you can say phase differences, must be coherent, you can say. What do we mean by this? Okay, so for example, we have a wave in here, or two waves, let's say. So this is one of them. Let's use a different color here. So this is one of them. Okay, and then the other one that we have, let's say, this is the other one here. Okay, now as long as we have this, you can see that the pattern that happens, we will have a constant or you can say constructive interference. The reason why constructive, because you can see these two are both, or just simply the phase difference between the two is 0. And of course, you can say these two waves have the same wavelength as well. That is one thing. Same frequency, you can call it T if you want to. Okay, but what happens if we, for example, let's say the phase difference between the two is not constant. So for example, up to this point is this, and then this is what happens later on. So what do you notice here? So you can see here, at this point, of course, you might get a constructive interference, sort of constructive, but then at this point here, you might, this kind of like you can say, thingy, it is going to change here. So let's use a different one here, perhaps. Okay, so we said up to this point here, okay, this is constructive, but you can see here, at this point and forward here, these two waves are not coherent. What does it mean that are not coherent? That means the phase difference between the two are changing here. And as long as they're changing here, that means, of course, now at this point, they might be constructive, this point here, a little bit constructive, but you can see what happens here. So this 2 points is almost like total destructive interference. And of course, at some other points, it could be partial destructive interference. And of course, so to make it short, we will not get a constant constructive or even destructive interference here. So in order for whatever the phenomenon that is happening, whether it is constructive interference or destructive interference, you must have a fixed phase difference. That fixed phase difference, you can call it coherence. Yeah? Okay, so if the two waves are coherent, have the same phase difference along the way all the time, then of course we can have constructive interference if it was constructive, or destructive interference if it was destructive. But if the phase difference changes between the two, then of course this will not continue, and that is not the condition for continuous constructive or destructive interference. That was the first thing, or the first term that you need to know. Okay, now another term that we have, for example, we have, by the way, that is something called coherence. So what is coherent? The correlation between the phases of two or more waves. What do we mean by this? Take a look. Now we'll say two waves, that'll be the continuation of this, or the explanation of the first point. Two waves are called coherent or are coherent if they have a constant, a fixed phase difference, and usually achieved by having the same frequency and you can say a fixed phase difference as well. That is when we call it a coherent, or two waves are coherent. That means they always, let's say, move with the same, let's say, you can say the same, or with the same, you could say, if I call it, I don't know, same wavelength and same frequency, let's say relative to one another. Okay, that is basically coherence. We have another term, we call it in phase. The phase difference between the two waves will be normally 0, yeah? It could be, of course, 360 degrees as well, and of course it could be multiple of that, but we just go with a 0 degree and that's it, yeah? So that is, when this happens, we call the two waves the waves, or the two waves are in phase. Could be more than two, but we'll just take two for now. What do we mean by if they're out of phase here? When we say out of phase, we normally, by the way, any angle, if the two waves are not, let's say, in phase, which is let's say the angle is not 0 or not 360, then any angle between the two, it is called out of phase, because when we say in phase, that means they have the same phase difference. So any change in that, of course, it is shifted from that, deviated from that, we call it out of phase. But here, for these, let's say, concepts and on, of course, whenever we say out of phase, we basically mean that the phase difference between the two is 180. Otherwise, any angle between, or let's say, any angle change or phase change between 0 to 360, that is considered out of phase. But once again, for the sake of these concepts, when we say out of phase, we just mean by the two waves are out of phase by 180 degrees here. Okay, so another point for this regarding regarding the study tip says, generally, that's what I have said, any phase difference between 0 and 360 degrees is considered out of phase, but here it is used specifically for phase difference of 180 degrees here. Now, interference of light. How does light interfere here? That is a very good question. Now we said for the interference to continue or to have a stable interference, we must have the same phase difference, and you can say, which means the same frequency and wavelength, correct? I mean, same phase difference. That means the two waves must have the same phase difference along the way. Let's say along the their propagation, let's say. Okay, but take a look. We have different lights, yeah? For example, we have a white light, the light that we get from a sun, for example, or the light that we get from a light bulb. Those lights, of course, these are polychromatic. That means not monochromatic, poly. That means there are a group of colors, basically, yeah? And of course, if we have a group of colors, what are the colors of light, let's say? And of course, if you want to let's say, name them in order, we can go ahead with this letter, yeah? Roy, of course, we can say Rho, G, Biff, yeah? That is red, orange, yellow, green, blue, indigo, and violet, yeah? We know that red has the longest wavelength and violet has the shortest wavelength. In terms of energy, we can say violet has the least, let's say, or the shortest wavelength. That means the highest frequency, the highest energy. Red has the longest wavelength, the lowest frequency, let's say, and of course the least energy as well. So because we have different colors, that means we have different frequencies. And of course, different frequencies, that means it is not going to be coherent because the phase difference between the two will change. Now we have, let's say, another type of light. If it is a single color, that is called, for example, light from a laser, that is monochromatic. Mono, that is a single color, we can say. And if it is a single color, we'll have the same, let's say, phase difference and the same frequency and wavelength. That can be called coherent, yeah? And of course, because you can see, they will maintain a constant phase difference and phase difference along the way. So that is called coherence, you can say. So far, if it is polychromatic, like the white light, we have a bunch of colors, we have multiple wavelengths, so of course not coherent, okay? So remember this, no coherence for this one. If it is a laser light, single color light, single wavelength, you can say, so we have a constant phase difference, so this can be called coherence. Okay, now we have another type of light, for example, if it is a light from LED light. Okay, for example, let's say if you have a white light in the room, let's say, that is a white light, yeah? This white light is also not coherent. Why? Because the reason why it is not coherent, because they don't maintain the same phase difference between the two. As you can see here, all these waves are, you can see, one of them is ahead of the other one, so they don't maintain a constant phase difference. So if that is the case, then will not be called or considered coherent here. So we call them non-coherent. So the only coherent light wave is the light from a laser. So remember this, for two waves to produce a stable interference pattern, the phase difference, or you can say the phases of the individual waves must maintain or remain unchanged relative to one another. Okay, now we have a very good question here. It says, why when two light bulbs are placed side by side, no interference is observed, even if the lights are of the same color? So let's say we have two white lights. You have two, let's say, red lights, and not laser light though. Okay, red light from any light bulbs, let's say, or if you have any two other lights, why don't we see the interference between these two lights, okay? The reason why we don't see them is because even though they might have the same frequency, let's say, yeah? So let's say they have the same frequency, but do they have the same phase difference? That is the question here. So let's say this is the light from one of them, okay? This is the light from one of them. And of course, for the other one, we can have, let's say, it is clearly they have the same wavelength and frequency as well. But if the phase difference between the two, or if these two are not coherent, let's say, we could have, let's say, something like this. Let me start here so that we can have something like this, yeah? So as you can see here, at some other points here, maybe this is more like a destructive one here. So let me redraw this one. Maybe at some point here, we can have not this precisely here. Okay. We could have done a little bit more. So you can see at some points, maybe they are coherent in phase, but some other points, they're not in phase anymore. So if they're not in phase anymore, maybe we'll see, maybe there is, of course, there is an interference here and maybe up to this point. But once it gets to this point here, at some region there is constructive, some other region there is destructive. So you can see the interference is not stable. It is not going to continue with only a constructive or destructive interference. So this is why you don't see a stable interference between these two light bulbs, even though they have the same color, let's say, or the same frequency. So the reason that causes this, the two waves are not, let's say, in phase or out of phase, let's say, along the way. So when this happens, we say the two waves are not coherent because they don't keep the same phase difference. So the difference, or you can say the phase difference between the light waves from one bulb is not constant. Random changes occurring to the light from one bulb do not necessarily happen to the other light bulb, yeah? So the light waves still interfere, but the condition for interference change with each phase change, and therefore no single interference pattern is observed. So light sources of this type are called incoherent. Okay, now we have another question which is also very important. Says what? Says, because of their great distance from us, stars are essentially point sources of light. If two stars were near each other in the sky, would the light from them produce an interference pattern? Explain your answer. Imagine we have a sun, yeah? We get light from the sun. Sun is pretty much, we can say it's not that close, but compared to other stars, it's close enough to us. So imagine or assume that we have another sun, or there's another star right next to sun. That would be the two stars. And of course, they both have, let's say, white light, or you can consider it yellow light as well. So here's the question. Will these two stars, or the light from these two stars, will they interfere constructively or completely destructively? The answer is no. Why? Because not necessarily these two light bulbs will have or maintain the same phase difference. And if they don't maintain the same phase difference, then clearly there will be no, let's say, it's not going to be, let's say, a stable constructive or destructive interference. So we'll just say it will be not observed to make it short for you. So the answer is going to be no, because the light waves are incoherent, even if they have the same color, by the way. Okay, so demonstrating interference. How do we demonstrate? How do we represent or show interference, let's say, on a screen, let's just say. So these are the procedures that we can have, but of course, I'll show you what happens here first of all, yeah? So let's say this is how it works. We have, let's say, a light, could be from a source, and then we will have, let's say, one slit. Light from this slit, of course, is going to spread, and then after that it falls into another slit that has two gaps here, and then here we have a screen here. Okay, so what exactly happens here? Or why do we use this setup here? So the first one, clearly light. Let's use a different color. Okay, let's use this color now. So light from this one, of course, will spread, yeah? And then after that, light from this will spread, or you can say after the light leaves this gap, it will diffract, it will bend, yeah? And of course, using Huygens principle, says that every, you can say, every part, or you can say every bit of, you can say, of light on these wavefronts can be considered as a secondary source, as almost like the light are coming from those. And I'll tell you why we have, or we should use this one. So light keeps spreading here. Then after that, you can see the reason why we'll use this, the first slit here, so that once the light, for example, spreads after this, we get the same light here. So whatever the light or whatever the change that happens to the wavelength here, okay, now we're using the single color, by the way, okay? So whatever the change that is happening to the light, of course, this change, of course, will be the same everywhere along the propagation of light. So after this light, of course, will re-spread, or let's say after it passes through these, for example, slits here, of course, it will spread again here. So let's say this is the first one here, okay, and of course it continues, and let's draw the second one as well. So this is, because remember, the light spreads as if, for example, this was the source of the light here. And then, using a different color here, let's use red one perhaps here. So now light would, of course, from this slit, of course, spread again too. So this is what happens here. Maybe the drawings are not precise, but look, every single point that these two lights, you can say, interfere here, these are, or you can say any point you take here, these are called constructive interference. In another word here, when the light, for example, reach these points together, they have the same phase difference. And if they have the same phase difference, then we've mentioned earlier here that whenever, for example, light waves have the same phase difference, of course, then they will interfere constructively. And don't forget, this is the light of the same color, but I've used different colors so that you see the difference between the light that is spreading from one slit here and, of course, with the other one as well. So as a result, what do we get on the screen here? As a result, on the screen, of course, we get a bright, you can say, spot on the screen here. This bright spark, of course, you can call it central maximum here, okay? Or sometimes you can call it the 0th order here. And I'll explain what is 0th order here. Okay, because let me talk or go to the sides here. So the first one is going to be bright, okay? And then the one right next to it is going to be dark in here. And of course, we get another bright here, okay? And of course, another bright here. Of course, there is dark regions in between, okay? And of course, this one here. And of course, we do have the same thing below this one as well. So these you can see spots that have kind of like use a rectangle for that, or you can say square here, more like a rectangle, not a complete circle, but I mean square. But I hope you understand what I'm drawing here. So these are bright, okay? These are bright spots here. These bright spots are called bright fringes here. So what happens exactly at these bright fringes? Whenever lights fall on the screen at these regions, they fall, or you can say they have the same, phase difference, by the way. And if they have the same phase difference, they interfere constructively, so we get bright fringes here. But this one, of course, it is the brightest among all the other ones. As we move further from the center, of course, the brightness becomes dimmer and dimmer and dimmer. What about like in between these like boxes that I've drawn? In between these boxes here, the light, or you can say one of the light would travel half a wavelength, or you can say an extra half a wavelength compared to the other one here. So at these regions here, they interfere destructively, so we get dark fringes here. So we have two regions now, you can say. Those regions that are bright, and of course those regions that are dark. So I'll write the D here for the dark, and of course B on the other side. These are for bright fringes here. So of course we're going to give names for these, like so that we can order them for easy calculations, of course. So we call the one that is at the center, we call it M, by the way, and M is the order of magnitude here. So the first one, or the one that is at the center, it is called 0, okay? So we can call it 0th maximum. That'll be an order of magnitude. This one, the one that is above, we can call it positive 1 here, or M equals to positive 1. The one that is above that, that is positive 2. The one that is above that, of course, is positive 3 and all that. So these numbers, we give them according to the central bright maxima, you can say. What about the lower one here? You can call this one -1, -2, -3. These negative, of course, -3, that means if you're going to consider this positive, the other side will be negative. But in calculations, of course, we're not going to write negative, because these negative are just to categorize which side you're talking about. Otherwise, we don't have anything such negative here. Or if you use something like as a number line, this side is positive, the other side is negative, just to know so that how far you are from the central maxima, and of course whether you're above or below that. This negative indicates that one. Otherwise, we don't use that in calculation. So this is basically what happened. Like I said here, for those bright fringes here, all the waves, or you can say for the central ones, very important. When we have, if I do this one here, when a wave, for example, is traveling all the way to the central one here, and then of course we have another wave here, once they reach here, they have the same phase difference here. Or you can say the phase difference between the two waves, once they are, let's say, reaching to the central maxima, the phase difference between the two is 0. What about this one here? The phase difference, of course, it is 0, but one of the waves has traveled one extra wavelength, or you can say 2 pi, according to, let's say, to the waves, let's say. That would be the, we have a path difference, and of course we have a phase difference. So you can say the path difference for one of them has traveled one extra wavelength. So of course it's going to be one of the wave, or the path difference, the phase difference for one of them is 2 pi, which is the same as 0 or 360. And then the other one here, one of the wave has traveled, let's say, 2 wavelengths here. And of course, which wave would it be? Of course it is this one, because it is further here, you can say. Okay, that is for that. That is in short, yeah? So this would be the explanation of all that. So once again, if when the waves fall on the screen, if they are in phase or if they fall on the face in phase, that is constructive interference, that is a bright fringe, and if not, it is a destructive interference, that is a dark fringe here. This is what we get as a result, but remember, this is what we get if we use a single color, let's say. So all these colors, or you can say the colors that we have, you can see that these are all the same, yeah? And of course, but the central maxima, of course, it is brighter compared to the other one. What happens if we use a colorful, or let's say if we use white light here? You know that white light is a combination of all the 7 colors that we've mentioned, yeah? RGB. And then if you use that one here, then this is what we get as a result. You see that the maximum, or the central one, it is white. Why? Because all the waves that are falling or reaching this are in phase, of course. As a result, we get white light here. But of course, on the other side, you can say, or on either side, of course, we get a bunch of colors, yeah? As you can see here, you can say it starts with violet, and of course, it ends up with red. Why red? Because we have something, or an equation that I'm going to tell you later, and that is what we're going to use. For example, we'll say d sine theta, okay? We'll say d sine theta equals to m lambda here, okay? And of course, this d sine theta, you can call it, this is, it is equal to the path difference here. And of course, this m, that'll be the order number, and this is the wavelength. So as you can see here, this sine theta, that'll be the angle between, if we go back to the other one here, that'll be the angle, let's say, between this one here, okay? Let's say, starting from the slit here to the let's say M1 or M2 or M3, depends on whether, let's say, we're considering the bright fringe or the dark fringe one here. So, but that is the angle. So clearly, if I use this one, d sine theta here equals to m lambda. In another word, the bigger the lambda or the wavelength, the bigger this angle is. So if I have, or compare, let's say, red all the way to violet, of course, red has a bigger wavelength. That means red light would deviate more. So if I use something like this here, so let's say this is the central, and this is the first bright one, okay? So if I have a bunch of colors starting from all this, of course, violet must be here, red must be there. Why? Because that is the only case where it makes sense when we say, so if we take, let's say this is the bundle that we get, correct? So, and this is the angle. As you can see here, the angle for violet, of course, it is going to be smaller because the wavelength is smaller, but then you can say the angle for red must be bigger because it has a bigger wavelength. And this is the whole thing, of course, you can say it is a bright spot on a screen. Okay, some of the ways that 2 coherent waves leaving the slit can combine at the viewing screen. I believe this is where we're going to stop for this session. Next session, inshallah, we'll continue from this and forward, and we'll continue with this. Till then, keep practicing, and I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.